Now, dear students, let's start new chapter, chapter 5, work, energy and power, right? Now, work, energy and power, these are the physical quantities. Later on, we will discuss the definitions of these quantities and detailed discussion related to all these will be carried out. First, we will discuss the scalar product of vectors, right? In previous chapters, we discussed about vectors and we discussed that we have to study about the vector algebra. And in vector algebra, we have to discuss summation of vectors, subtraction of vectors and multiplication of vectors. Division of vectors are not defined, right? Now, in previous chapters, we discussed about summation of vectors and subtraction of vectors. Now, in this particular chapter, we will discuss about the product of vectors or multiplication of vectors. There are two types of multiplication of vectors. One that is the scalar product and another one that is the vector product. Let's first discuss scalar product of vectors. So when the product or multiplication between vectors is carried out in such a way that the result is a scalar quantity, then it is called scalar product of vectors. This scalar product of vectors is represented by the symbol of dot between vectors. So it is also known as dot product. Now, we can carry out the scalar product between two vectors, between three vectors, between four vectors. But here, we will restrict our discussion for scalar product of two vectors. Now, see here. Suppose we have two vectors, vector A and vector B. Suppose we represent both the vectors from the same origin O, right? Then, here we can see the angle between these two vectors is suppose theta, right? Now, how the scalar product between these two vectors that is defined? The scalar product between these two vectors A and B, that is defined as A dot B equal to magnitude of A into magnitude of B into cosine of the angle between these two vectors. Simply we can write vector A dot vector B, that is AB cos theta, where theta that is the angle between A and B. Okay. Now here we can see this thing. See, on right hand side here, A that is the magnitude of vector A, B that is the magnitude of vector B, and cos theta. All are the scalar quantities. So result of this one will be a scalar quantity. So we can say this is the scalar product of two vectors. Now here we represent it by the symbol of dot we discussed. So it is known as dot product also. Now see here. In this figure, suppose we draw a normal from the head of A to this vector B, as well as a normal from the head of B to vector A. Then we will get these elements OM and ON, right? Now see here. When we write A dot B, that is AB cos theta, then we can write this one as A dot B equal to B into bracket A cos theta. Clear? Now suppose we take here cos theta, right? Then we can write cos theta, that is this. First we take this adjacent, then adjacent upon hypotenuse. So adjacent is OM and hypotenuse, that is magnitude of vector A. So we can write cos theta, that is OM upon A. So OM that is equal to A cos theta. Clear? So now here A cos theta that we can replace by OM. So we can write A dot B that is B into OM. It implies that we can write B that is magnitude of vector B and OM that is the projection of vector A on B, or we can say the component of vector A in the direction of vector B. Similarly, we can write A dot B that is A into B cos theta that is A into ON. So that is magnitude of vector A into projection of B on vector A. So now in broad sense we can give the definition of scalar product of two vectors like this. The scalar product of two vectors is the product of the magnitude of first vector or any one vector with the projection of second vector or other vector on the first vector or in the direction of first vector. So this one is the scalar product of two vectors. Clear to all of you? Now next topic, that is properties of scalar product of vectors. Now this is very important thing because the properties of scalar product of vectors, that is very useful to solve different problems as well as MCQs, right? Now see here, first thing, the commutative law. We write A dot B that is AB cos theta. So we can write it as BA cos theta also. So that is B dot A. It implies that we can write A dot B that is equal to B dot A. So we can say this thing, the commutative law holds for the scalar product of vectors. Then after the distributive law, right? Suppose we have A dot B plus C. Then simply we can simplify it like this, A dot B plus A dot C, right? So distributive law also holds in the scalar product of vectors, okay? Now suppose A and B are parallel to each other. If A and B are parallel means theta that is 0. So if theta that is 0, then cos theta that is cos 0 that is equal to 1. So in that particular case simply we can write A dot B that is AB. Clear? Now suppose we take A dot A, then vector A dot vector A that is simply we can write A into A that is A square. So we can write magnitude of A that is under root A dot A. It implies that if we have vector and if we want to find its magnitude, then easily we can calculate it with this relationship. Okay? Now, magnitude of a vector is equal to the square root of the scalar product of vector with itself, right? Then after, if A and B are perpendicular to each other, if A and B are perpendicular to each other, then theta that is equal to 90. So A dot B equal to AB cos theta that is cos 90 that is equal to 0. It implies that here A dot B that will be equal to 0. So if two vectors are perpendicular to each other, always their dot product will be 0. Or in other words, we can say if dot product of two vectors comes to 0, then we can say these two are perpendicular to each other. Okay? So scalar product of two mutually perpendicular vectors, that is always 0. Clear? Now, scalar product of unit vectors in Cartesian coordinate system. We know this thing, we have three axes x, y and z in Cartesian coordinate system. And we have I caret, j caret and k caret unit vectors in the direction of x, y and z respectively in the Cartesian coordinate system. So between these unit vectors I caret, j caret and k caret, how the scalar product is carried out. Okay. Now let's first think about I dot I. So here we can write, suppose we have I dot I. So magnitude of I caret 1, magnitude of I caret 1. Now angle between vector and vector itself, that is 0. So we can write cos 0, so that is equal to 1. So I dot I caret, that is 1. So similarly we can write j caret dot j caret and k caret dot k caret, that is also equal to 1. But suppose we take I caret dot j caret, magnitude of I caret 1, magnitude of j caret 1, and angle between I caret and j caret, that is 90. So this is equal to 0. So we can write I dot j, that is equal to j dot k, that is equal to k dot I, and that is equal to 0. And here we can write j dot I, that is equal to k dot j, that is equal to I dot k, that is also equal to 0. Simple thing. Clear? Okay. Now see here. Scalar product in terms of Cartesian components of vectors, right? So in Cartesian component form we write the vectors A and B as vector A equal to AXI caret plus AYJ caret plus AZ k caret, and vector B that is equal to BXI caret plus BYJ caret plus BZ k caret. Okay. Now let's take dot product between these two vectors in component form. So A dot B. So in first bracket we will take vector A in component form, dot in second bracket there is the vector B in component form. Right? Now here simply we have to carry out the calculations like this. First we have to multiply AXI caret with these three components. Okay. But here be careful, this particular symbol of dot will be placed between vectors only, because dot product is defined for vectors only. It is not defined for scalars or scalar and vector. Okay. So see here how we will write it. First AXI caret is multiplied with these three. So AX BX I caret dot I caret. Then AX BY I caret dot J caret. Then AX BZ I dot K caret. Similarly, multiply AY J caret with these three. So we will get AY BX J caret dot I caret. AY BY J caret dot J caret plus AY BZ J caret dot K caret. Then multiply AZ K caret with these three. So we will get AZ BX K caret dot I caret plus AZ BY K caret dot J caret plus AZ BZ K caret dot K caret. But here we discussed the scalar product between unit vectors. So from that, substitute the values here in this particular one. So here I dot j, I dot k, j dot I, j dot k, k dot I, k dot j will be cancelled. And this I dot I, j dot j and k dot k, that will be equal to 1. So we can write simply vector A dot vector B, that is equal to AX BX plus AY BY plus AZ BZ. Clear? Now see, if we want to find the angle between two vectors are given to you in Cartesian component form, suppose, right? And you want to find the angle between two vectors. Now we know A dot B, that is AB cos theta. So we can write cos theta, that is A dot B upon AB. So in Cartesian component form, we can write A dot B, that is AX BX plus AY BY plus AZ BZ. And magnitude of A, that is under root AX square plus AY square plus AZ square. Similarly, magnitude of B, that is BX square plus BY square plus BZ square. So here, using this particular formula, easily one can find the angle between two vectors also. Clear? Now, suppose we have any scalar quantity, lambda, and we multiply it with A dot B. Okay? So here, when lambda is a scalar quantity, then you can simplify this type of problem simply like this. Suppose first you take product of lambda with B, and then after if scalar and vector is multiplied, it is simple product and the resultant will be vector quantity because one vector is there. And then after take dot product of this new vector with A, or first multiply lambda with A, you will get a new vector, right? And then take dot product of it with B. If you multiply this one by lambda, you know magnitude of vector A will be changed, direction will not change. Clear to all of you? So this is the properties. Dear students, now next topic, that is vector product of two vectors. When the product or multiplication between vectors is carried out in such a way that the result comes to vector quantity, then it is known as vector product of two vectors, right? Now here, vector product of two vectors, that is defined as A cross B, vector A cross vector B, that is magnitude of vector A into magnitude of vector B into sin theta into n caret, where theta, that is the angle between vector A and vector B, and n caret, the unit vector that is in the direction perpendicular to vectors A and vector B both. It implies that it is perpendicular to the plane formed by vector A and vector B. Now the question is this one, how to decide direction of this unit vector n caret? Because if we think about any plane, then there are two directions perpendicular to the plane. One is like this, another one that is below this one. Okay? Now, the direction of n caret means this unit vector appearing in the definition is represented by right hand screw rule. Now see here, this one is also represented as cross product because here the symbol of cross is represented between vector A and vector B. So it is also known as cross product. So remember this thing. Now suppose we have vectors A and vector B as shown in the figure, and between A and B the angle is theta. Now what we have to do? We have to place right hand screw perpendicular to both A and B. Suppose, say here, this one is vector A and this one is vector B. Now we have to place right handed screw perpendicular to both this one. Now we want A cross B. A cross B. So we have to rotate this right handed screw like this from A to B. From A to B. So when right-handed screw is rotated anti-clockwise, it comes out. So it moves in upward direction. So when right-handed screw is rotated from A to B, the direction in which it transfers, that is the direction of resultant vector of A cross B. And this particular direction can be fixed with the help of right hand rule, or we can say right hand thumb rule. See how we apply this one. So suppose again we think this one is vector A, this one is vector B. Now we want A cross B. So here we have to place our fingers in the direction from A to B like this. So the stretched thumb will give you the direction of resultant of A cross B. Or in other words, we can say the vector coming out from your right hand palm, that will give you the resultant direction of A cross B. Clear to all of you? Now see how we can apply this right hand rule or right hand thumb rule. See, suppose these are our vectors A and vector B. Then in the plane of vector A and B, what we have to do? We have to encircle our fingers from A to B, because we want A cross B. So encircle your fingers from A to B, then the direction of the stretched thumb, that will give you the direction of resultant of vector A cross vector B. Clear to all of you? Now properties of vector product of vectors. Now see, to fix the direction of resultant vector obtained by A cross B, we use right hand screw rule or right hand thumb rule. So easily we can understand this thing. If we rotate right hand screw from A to B, then the direction in which it transfers. And if we rotate it from B to A, then the direction in which it transfers, both will be opposite. It implies that if we take A cross B and then if we take B cross A, then we will not get the same result. So we can say A cross B is not equal to B cross A. Means vector product of two vectors is not commutative. Here magnitude wise A cross B and B cross A will be same one. Magnitude wise it is A B sine theta. But direction wise exactly opposite. So we can write A cross B, that is minus B cross A. Then distributive law, that as it is we can represent. Suppose we want vector A cross vector B plus C, then simply we can write first vector A cross vector B, then plus vector A cross vector C. So we can say commutative law holds for vector product of two vectors, right? Now, if two vectors are parallel to each other, or two vectors are anti-parallel to each other, so in that particular case, if parallel, then theta is 0. Then sine theta, that is equal to sine 0, that is equal to 0. So A cross B, that will be equal to 0. And if two vectors are anti-parallel, then in that case also sine theta, that is sine 180, and that is equal to 0. So if two vectors are parallel or anti-parallel, their cross product, that will be always 0. And remember this thing, when two vectors are perpendicular to each other, their dot product is 0. This thing is very important in problem solving as well as MCQ solving. Now if A and B vectors are perpendicular to each other, then sine theta, that is sine 90, that is 1. So A cross B, that is A B sine 90 n caret. So simply we can write sine 90, that is 1. So this is equal to A B n caret. Now vector product between unit vectors of Cartesian coordinate system. We know in Cartesian coordinate system, I caret, j caret and k caret unit vectors are respectively in the directions of x-axis, y-axis and z-axis. Suppose here we take I cross I, then we can write magnitude of I, that is 1, magnitude of I, that is 1, then sine theta, that is sine 0. In this case, theta will be equal to 0, sine 0, 0. So I caret cross I caret will be equal to 0. Similarly, j caret cross j caret as well as k caret cross k caret, that will be equal to 0. But suppose we take I caret cross j caret, then I caret cross j caret, so we can write here, see, suppose we consider that clockwise circle like this, okay? Then here remember, I caret cross j caret, that is equal to k caret. Why? Because magnitude of I caret is 1, magnitude of j caret is 1, I caret and j caret are perpendicular to each other, so sine theta, that is sine 90, that is 1. And in definition we have n caret, that is perpendicular to both the vectors. Here perpendicular to I caret and j caret, that is the k caret. So here we can write I cross j, that is k. Now in this way, if you think clockwise for this circle, then easily you can remember I cross j, that is k, j cross k, that is I, and k cross I, that is j. Now if you take anti-clockwise, right, then the result will be with negative sign. See here, I cross j, that is k, so j cross I, that is minus k, j cross k, that is I, so k cross j, that is minus I, k cross I, that is j, so I cross k, that is minus j, right? Now the vector product between vectors in the Cartesian component form, okay? So in Cartesian component form we write vector A, that is equal to axi caret plus ayj caret plus az k caret, and vector B, that is equal to bxi caret plus byj caret plus bz k caret. Now vector A cross vector B, that is equal to, in first bracket we have to take vector A in the component form, cross in second bracket vector B in component form. Now here carry out this multiplication in this way. First take axi caret and multiply it with these three one by one, okay? Here the symbol of cross, that will be placed between vectors only, because cross product is defined for vectors only. So first step will be ax bx I cross I. Here you have to maintain the order. These unit vectors are first, so in multiplication you have to represent this one first and then this one. So ax bx I cross I, then ax by I cross j, then ax bz I cross k, this third one. Then after sorry, second one, AY, BX, J cross I. Then AY, BY, J cross J. Then AY, BZ, J cross K. Then third one, AZ, BX, K cross I. AZ, BY, K cross J. AZ, BZ, K cross K. Now see, we already discussed about the vector product between unit vectors. So substitute those values. Now we discussed that thing, I cross I, J cross J and K cross K, that is 0. So this particular term, this one and this one will be cancelled. And now substitute the values of I cross J, I cross K like this. So here I cross J, that is K. Then I cross K, that is minus J. Then J cross I, that is minus K. Then J cross K, that is I. Then K cross I, that is J. And K cross J, that is minus I. Now here, take I caret common. Then we will get two terms in the bracket, AY BZ minus AZ BY. Then after take J caret common. So we will get AZ BX minus AX BZ into J caret. Plus now take K caret common. So AX BY minus AY BX K caret. So this one is the result of A cross B. You have to remember in this particular manner this equation, or you can represent this one in the form of determinant. So vector A cross vector B, that is determinant I caret, J caret, K caret, AX, AY, AZ, BX, BY, BZ. Now mathematics students know what is determinant and how to solve it. But biology students don't know, right? So if you remember in this particular manner, then you have to understand how to solve this determinant. Okay? So see here. Now actually in this second step, J caret is taken common. So when we take J caret common, so AZ BX comes first, then minus AX BZ. But when we solve this determinant at that time, here J will appear with negative sign. So remember this thing, in that particular case, when you take J that is with negative sign, then AX BZ will come here first, then minus AZ BX. Now let's understand how to solve this particular determinant. See, now this one is our determinant. I, J, K, AX, AY, AZ, BX, BY, BZ. Now for determinant, this one is known as row, and I, J, K are the components of first row, AX, AY, AZ are components of second row, BX, BY, BZ, that is component of third row. This one is the column. So component of first column I caret AX BX. For second column J caret AY BY. Then for third column K caret AZ BZ. Now first forget about sign. Later on we will discuss about the sign plus minus. First think like this. First take this component I caret from first row and first column, right? Now this particular component appear in the first row and first column, so we have to discard this row and this column. So if we discard this one, then we will have this particular 4 components. Then we have to take product of this one. AYBZ on right side, then after minus AZBY, like this. Clear? So I caret into AYBZ minus AZBY. Right? Now this first thing. Then after, take this J caret. So J caret, that is in first row and second column. So discard first row and second column. So now we will have these four components. So again take the product of these two components in right direction, then minus in left direction. So J caret into AXBZ minus AZBX. Clear? Then after, think about this third one, K caret. So discard again this first row and third column. Now we have these four components. So again take product in right side direction, AXBY in cross, then in left direction in cross. So K caret into AXBY minus AYBX. Clear? Now simplification is carried out. Now we have to give signs. So here represent this one with positive sign. So first positive sign, then negative sign, then positive sign. Right? And math students will study further how to solve this entire one with these all 9 components. But that is beyond our scope. So clear to all of you how to solve this one. Now example 5.1. Find the angle between force vector F equal to 3I caret plus 4J caret minus 5K caret unit and displacement vector D equal to 5I caret plus 4J caret 3K caret unit. Also find the projection of vector F on vector D. Okay. Now see here. First we have to find the angle between these two vectors. Now as per definition of dot product, we can write F dot D, that is F D cos theta. So cos theta, that is F dot D upon F D. So here F and D are given to you in component form. So first find out F dot D, that is Fx dx plus Fy dy plus Fz dz, right, in component form. So Fx, that is 3, dx, that is 5, then Fy, that is 4, dy, that is 4, then Fz, that is minus 5k, dz, that is 3. So its answer will be 16. Now magnitude of F, that is under root Fx square plus Fy square plus Fz square, that is under root 3 square plus 4 square plus minus 5 square, this will be root 50. Similarly, magnitude of D, that is under root dx square plus dy square plus dz square, it is under root 5 square plus 4 square plus 3 square. See this one, solve it, you will get root 50. Now cos theta, that is F dot D upon Fd, right? So we can write F dot D, that is 16 upon root 50 into root 50. So this is 50. Solve this one, you will get the answer 0.32. Clear? So theta, that is cos inverse 0.32. See this one in the table of natural cosine, you will get the angle 71 degree and 16 minute. Now we have to find the projection of F on D. So projection of F on D, that is F cos theta, right? So projection of vector F on vector D, that is F cos theta. F, that is root 50, cos theta, that is 0.32. So this will be 2.26 unit. Clear? Dear students, now next topic, that is vector product of two vectors. When the product or multiplication between vectors is carried out in such a way that the result comes to vector quantity, then it is known as vector product of two vectors. Right? Now here, vector product of two vectors, that is defined as A cross B, vector A cross vector B, that is magnitude of vector A into magnitude of vector B into sin theta into n caret, where theta, that is the angle between vector A and vector B, and n caret, the unit vector that is in the direction perpendicular to vectors A and vector B both. It implies that it is perpendicular to the plane formed by vector A and vector B. Now the question is this one: how to decide direction of this unit vector n caret? Because if we think about any plane, then there are two directions perpendicular to the plane. One is like this, another one that is below this one. Okay. Now the direction of n caret means this unit vector appearing in the definition is represented by right hand screw rule. Now see here, this one is also represented as cross product, because here the symbol of cross is represented between vector A and vector B. So it is also known as cross product. So remember this thing. Now suppose we have vectors A and vector B as shown in the figure, and between A and B the angle is theta. Now what we have to do? We have to place right hand screw perpendicular to both A and B. Suppose, say here, this one is vector A and this one is vector B. Now we have to place right handed screw perpendicular to both this one. Now we want A cross B. A cross B. So we have to rotate this right handed screw like this from A to B. From A to B. So when right handed screw is rotated anti-clockwise, it comes out. So it moves in upward direction. So when right handed screw is rotated from A to B, the direction in which it transfers, that is the direction of resultant vector of A cross B. And now see how we can apply this right hand rule or right hand thumb rule. See, suppose these are our vectors A and vector B. Then in the plane of vector A and B, what we have to do? We have to encircle our fingers from A to B, because we want A cross B. So encircle your fingers from A to B, then the direction of the stretched thumb, that will give you the direction of resultant of vector A cross vector B. Clear to all of you? Now dear students, next topic, that is work. Now work is a physical quantity which is defined as the product of the component of force in the direction of displacement and the magnitude of displacement, right? So this one is the definition of work done. Okay. Now see here, suppose we have a block placed on the horizontal surface, right? And as shown in the figure, force F is applied on it in the direction making an angle theta with horizontal direction. And suppose under the effect of this particular force, this particular block is displaced by D. So here the component of the force in the direction of the displacement that we can write, that is F cos theta. Okay. Now, as per definition of work done, the product of component of force in the direction of displacement, so that is F cos theta, and magnitude of displacement, that is D. So we can write W, that is F cos theta into D, or you can write that is FD cos theta. Now we already studied about the dot product of two vectors. Suppose we take vector A dot vector B, then that is AB cos theta. So similar to that, we can write this FD cos theta, that is vector F dot vector D, right? Now, unit of force, that is Newton, and unit of displacement, that is meter. So unit of work done, that is Newton into meter, and this particular unit Newton into meter, that is called joule, and its dimensional formula, that is M1 L2 T minus 2. Clear? Now let's discuss some special cases of work done. Suppose, see here, W, that is FD cos theta. In this theta, that is 0, it implies that if force and displacement both are in the same direction, then if theta is 0, cos theta, that is cos 0, that is 1. So W, that is F into D. Now if theta, that is equal to pi by 2, it implies that if force is perpendicular to the displacement, then in that particular case cos theta, that is cos pi by 2, and that is equal to 0. So work done, that is 0. Okay. Now here, if theta, that is pi, it implies that force and displacement are in mutually opposite direction. Then in that particular case, cos theta, that is cos pi, that is minus 1. So W, that is equal to minus F into D. So here, now in broad sense we can say if theta is less than or equal, 0 is less than or equal to theta is less than pi by 2. If this condition is satisfied, then in that particular case, the work done will be positive. Means if angle between force and displacement, that is either 0 or between 0 to pi by 2, then work done is positive. If work done is positive, then it is said work is done on the system. And if theta, that is between pi by 2 and pi or equal to pi, in that particular case your work done, that is negative, and it is said work is done by the system or body against the force. So this thing you have to remember carefully, because in MCQ or in any example, if it is given to you, the work done on the system, that is this much, then when you carry out the calculation, you have to take work done positive. And if it is given to you, work is done by the system, then you have to take that is negative. Then and there your answer will be perfect one. Clear to all of you? Now next topic, that is kinetic energy. Energy means what? Energy, that is nothing but capacity to do work. So capacity to do work of the object, that is known as energy. Then what is kinetic energy? So capacity of the object to do work by virtue of its motion, then it is known as kinetic energy. And this one is the scalar quantity. Now, how the kinetic energy is defined? So, definition of kinetic energy is given like this: half of the product of mass of the object and square of its velocity, that is known as kinetic energy. It is denoted by capital K of the body. So we can write kinetic energy K, that is equal to half mv square. If we multiply and divide by m, then we can write m square v square by 2m. But m into v, mass into velocity, that is known as momentum. So this numerator that we can write p square. So p square by 2m. It implies that we can write the equation of kinetic energy K, that is equal to either half mv square, or we can write K equal to p square by 2m. Clear? Now here p, that is linear momentum. Right? Now, the unit and dimension of the kinetic energy, obviously that will be equal to unit and dimensions of work done, because after all, kinetic energy or energy, that is capacity to do work. Clear? Now next topic, that is notions of work and kinetic energy. And the work energy theorem means how work and kinetic energy, that is associated with each other. Right? Let's discuss this thing. Now, as per definition, the work done under the effect of force F, that is W equal to vector F dot vector D, where D, that is displacement. Now we know this thing as per Newton's second law of motion. Force F, that is equal to ma. So we can write W, that is equal to m vector A dot vector D. But we already discussed about the equation of motion with constant acceleration. So we have that third equation, that is v square minus v0 square, that is 2a dot d. So here, if we replace this a dot d by v square minus v0 square upon 2, okay, then we can write W, that is m into v square minus v0 square by 2. Simplify this one. Then we can write W, that is half mv square minus half mv0 square. Here v, that is the final velocity, v0, that is initial velocity. So see, half of the product of mass and square of velocity, it implies that these both terms represent kinetic energy. But in first term, the velocity appears, that is final velocity. So we can say this first term, that is final kinetic energy, and this second term, in that initial velocity v0 appears. So we can say this thing, half mv0 square, that is the initial kinetic energy. So we can write W, that is k minus k0, and that is delta k. It implies that W, that is equal to change in kinetic energy of the body. Clear? K, that is final kinetic energy, k0, that is initial kinetic energy. So from this one, we can give the statement like this: the work done by the resultant force on the body is equal to the change in kinetic energy of the body. And this particular statement itself is known as work energy theorem. Clear to all of you? Now next is example 5.2. It is well known that a raindrop falls under the influence of the downward gravitational force and the opposing resistive force. The latter is known to be proportional to the speed of the drop, but is otherwise undetermined. Consider a drop of mass 1 gram falling from height 1 kilometer. It hits the ground with a speed of 50 meter per second. Then A, what is the work done by the gravitational force? B, what is the work done by unknown resistive force? First of all, the given data, that is mass is 1 gram, so that is 10 raised to minus 3 kilogram. Height h, that is 1 kilometer, so that is 10 raised to 3 meter. And the final speed, that is 50 meter per second. Initial speed, that will be equal to 0 here, obviously. Now, first we have to calculate work done by the gravitational force. Okay. So, work done by the gravitational force, that is mgh. Force, that is mg. And under the effect of this gravitational force, the distance travelled, that is h. Gravitational force, that is in downward direction. Displacement, that is also in downward direction. Clear? So, this work done, that is positive. So, m, that is 10 raised to minus 3, g 10, h 10 raised to 3. So, it is 10 joule. Now, second question is, we have to find the work done by unknown resistive force. So, resistive force, that is unknown. And resistive force, when it is unknown, how to calculate work done by it? Okay. So, here the work energy theory, that will be helpful to us. Okay. Now, see here. First, we calculate the change in kinetic energy of the drop. So, change in kinetic energy, that is half mv square minus half mv0 square. But v0, that is 0. So, half m, that is 10 raised to minus 3, and v square, that is 50 square, minus initial kinetic energy, that is 0. So, change in kinetic energy turns to 1.25 joule. Now, in work energy theorem, we studied this thing. The total work done, that is equal to change in kinetic energy. Now, here, total work done, that is work done by gravitational force as well as work done by resistive force. So, we can write here, as per work energy theorem, delta K, that is total work done. Total work done, that is delta K equal to Wg, that is work done by gravitational force, plus work done by resistive force on the raindrop. Clear? Now, see here. So, Wr, that is delta K minus Wg. Delta K, that is 1.25, Wg, that is 10. So, answer is minus 8.75 joule. See here, your answer is negative. Why? Because drop is falling in downward direction and resistive force, that is in the opposite direction of its motion. So, here resistive force and the displacement both are in mutually opposite direction. So, automatically our answer turns to negative value. Clear to all of you? Now, example 5.3. A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to the road is 200 Newton and is directly opposed the motion. Say it is given to you, it opposes the motion. Right? So, it is in opposite direction of the motion. So, A, how much work does the road do on the cycle? B, how much work does the cycle do on the road? Now, see, here displacement of the cycle, that is given to you 10 meter. Force, that is in the opposite direction of the displacement because it is opposing the motion, and therefore the cycle is stopped after skidding. So, here we can say the angle between force and displacement, that is 180 degree. So, theta, that is pi radian. Okay. Now, first, the work done by the road on bicycle, okay, or cycle. So, Wr, that is Fd cos theta, that is 200 into 10 into cos pi. So, that is minus 2000 joule. Okay. So, here the negative work done is representing the force is opposing the motion, and due to that the cycle is stopped. Okay. Now second question. How much work does the cycle do on the road? So work done by the cycle on the road. If here road exert 200 Newton force on the cycle, then as per Newton's third law of motion, cycle also exert the same amount of force on the road. So that is 200 Newton. Okay. So from Newton's third law, an equal and opposite force acts on the road due to the cycle, and its magnitude is 200 Newton. But here road is not displaced. So displacement of road, that is 0, and therefore we can say work done by the bicycle on the road, that is equal to 0. Clear to all of you? Now example 5.4. In a ballistics demonstration, a police officer fires a bullet of mass 50 gram with a speed 200 meter per second on soft plywood of thickness 2 centimeter. The bullet emerges with only 10% of its initial kinetic energy. What is the emergent speed of the bullet? Okay. So here it is given to you mass, that is 50 grams, so that is 50 into 10 raised to minus 3 kilogram. Initial speed, that is 200 meter per second. Final kinetic energy, that is 10% of initial kinetic energy, means it is 0.1 times Ki. So here first of all we have to calculate initial kinetic energy, right? So initial kinetic energy, that is half mvi square, half mass, that is 50 into 10 raised to minus 3, initial speed, that is 200, take square of it, you will get the answer 1000 joule. Now we have to calculate emergent speed, and here the information given to you, that is final kinetic energy, that is 0.1 times initial kinetic energy. So we can write K final, that is 0.1 Ki, so 0.1 into 1000, that is 100 joule. Now final kinetic energy, that is half mvf square, where vf, that is the final speed. So if we take vf is the final or emergent speed of the bullet, then K final, that is half mv final square, and that is equal to 100 joule, right? That we already calculated, that is 100 joule. Now substitute the value of mass and then make Vf as the subject of equation. So Vf, that is under root 2 Kf upon m, under root 2 Kf, that is 100, m, that is 50 into 10 raised to minus 3. When you solve it, you will get the answer 63.2 meter per second. Clear to all of you?